Dusty from Discovery Lab in Tulsa, Oklahoma for Discover at Home, a series of experiments and activities that you can do at home with a caregiver or parent. Our experiment for today is lava lamps. We'll be learning about density and chemical reactions. Let's talk a little bit about density. Whenever we talk about density, that means how close or how tightly packed something is. Everything in the world is made up of atoms. Those atoms can be very, very tightly packed or dense, or they can be spread way out. For instance, the air in this room, the molecules are way spread out. I can move all around and I barely feel myself bumping against them. In water, the molecules are a little bit closer. You can feel yourself pushing against them and they push back a little bit. And then a solid, like sand, their molecules are even closer. Do you think you could climb out of sand if you were all the way up to your neck? Might be a little bit hard. That's because the pieces or the atoms and molecules that make up sand are denser, are more tightly packed. I've got two things here. A balloon full of air and a metal ball. You can see they're about the same size, but they feel so much different. This one weighs hardly anything at all, whereas this one feels pretty solid. I've also got a whole bucket of water here. Now, denser objects are going to go down whenever they come against a less dense substance. For instance, my ball is denser or more closely packed than the air, so if I let it go, it's going to go down. My balloon goes down as well. That's because it's denser than the air around it. It has a balloon, whereas the air around it doesn't. So it gets pulled down. But if this was full of helium, it would go up. That's because helium is less dense or lighter than the air around it. So it goes up. I don't have any helium, but we're going to talk about that with our water. Now, if I drop both of these in my water, which one do you think is going to go to the bottom? The balloon, the ball, both of them? Let's find out. So if I drop my balloon in there, you can see it sits right on the top of my water. I know that my balloon is less dense than water. Water is denser because it wants to go up to the top, and the denser stuff wants to go to the bottom. Let's check my ball. Oh, he's definitely denser than water. Went straight to the bottom. Doesn't even try and float at all. So, denser materials want to go down, whereas less dense materials want to go up. Our experiment is going to be dealing a little bit with density. I wonder if you guys can spot which materials are more dense and which materials are less dense. Let's talk a little bit about chemical reactions, specifically acid-base reactions. How many of y'all have ever seen a volcano? Not like the big ones in Hawaii, but the science fair ones, where you take some baking soda and you put it inside and you pour vinegar over the top of it and it starts bubbling and fizzing all out. If you've ever seen one of those, you've seen an acid-base reaction. Acids and bases are opposites on a scale we call the pH scale. It goes from 1 all the way up to 14. The closer it is to 1, the stronger an acid it is. This would be things like battery acid, stomach acid. As you go up, we get things like malic acid and citric acid. Once we get to 7, that's where it is neutral. It's not an acid or a base. Pure water is neutral. It's not acid or base. As we go up from there, we get to more basic things, like soap and laundry detergent. Then we start to get to things that are really dangerous, like washing soda and ammonia and cleaners and stuff like that. Luckily enough, there's a few things that are on the safe side of things that we can experiment with. I've got an acid here. This is called citric acid. It's acid that comes from citrus fruits, like lemons, limes, oranges. It's what makes them so tart and sour. I've also got some baking soda. Baking soda is sometimes used as a cleaner. It helps us scrub things and get things nice and shiny, but it's not that strong, so it's not going to hurt us. But we can still have an acid-base reaction. Because they're opposites, whenever they mix together, they want to cancel each other out. So let's see that cancellation in effect. Now, the term for this cancellation is called neutralization. If you remember, water is neutral. They're trying to cancel each other out and get as close to pure water as possible. So there's my acid in the bottle. And let's see what happens when I pour some of my baking soda in next. All right, you guys ready for this? All right. 3, 2, 1. Well, nothing seems to be happening. Why do you think that is? The answer is because they're both solids. They're both powders. They're not really mixing. They're just kind of sitting beside each other. This is kind of a crystal, like sugar or salt. And this is more of a powder. They're just kind of resting. They haven't actually combined together to make a reaction. In order for any reaction to take place with acids and bases, you have to have at least a little bit of water. So let's add just a splash of water. There we go. So you guys can see we get some bubbling and fizzing happening inside my bottle. Now something fun's happening inside. Just listen real carefully, see if you can hear it. Can you hear that fizzing? What's happening is, as that reaction takes place, it's letting out tons of gas. Woo! Did you hear that? That was loud. This reaction is pretty cool. Literally, it's cold. It's making my hand feel cold. All those bubbles right there are an example of our chemical reaction taking place. Whenever the baking soda and citric acid mix together, they neutralize or cancel each other out. But that means that all the molecules and the atoms that make those molecules up have to change. In a chemical reaction, the molecules change into something new. The new thing they changed into was water and CO2. CO2 is the air that you breathe out. We breathe in oxygen and out CO2. But what does this remind you of? Have you guys ever seen anything that looks maybe bubbly and fizzy like this? If you said a soda, you're right. Whenever you open up a soda, it bubbles and fizzes like this. That's the same gas. That's CO2 gas escaping. Whenever you open that bottle, little bits of the gas is able to escape, but the rest stays dissolved inside the liquid. That's because sodas usually have sugar in them. It thickens it, and it makes them stick in there really, really hard. It's getting colder and colder the more the reaction takes place. That's because this reaction is endothermic. That means it needs to suck in some heat before it'll work. If this was too cold, it wouldn't work. It has to have enough heat to go. Kind of like how a fire doesn't work until it has enough heat. But fires get hot. This one gets pretty chilly. I'm going to see if I can get any more gas in there. Now if I feel this, I can feel it's getting really pressurized. It's getting tighter and tighter and tighter. Kind of like if you accidentally drop your bottle of soda and the bubbles kind of start rising and you're worried it's going to explode. Same thing's happening in here. The pressure's building up until it pops open. Now you can see my reaction has stopped or slowed down. So we're going to set it aside and we're going to move on to our lava lamps. Take a look at your Alka-Seltzer packet. If you look right here, it tells you the ingredients inside of it. It says it's got citric acid, aspirin, and sodium bicarbonate. Well, do you guys know what sodium bicarbonate is? That's a fancy word for baking soda. So the three things inside this are citric acid, aspirin, and baking soda. We don't care about the aspirin so much because we're not actually going to be eating this. It's just kind of a little extra thing that's inside of this. What's really important is the citric acid and baking soda. If I open this up, it looks kind of like a little puck or a little plastic disc. But if you crumble it, you can see it's actually that powder stuck together. Remember, baking soda and citric acid don't react when they're dry. We have to have some water. So these guys right here will never react unless they get some moisture. They can absorb moisture from your sweat, your skin, they can get some from the air, or we could just dunk them in some water. I drop this guy in here, you'll see he starts bubbling and fizzing. He's creating that CO2, or carbon dioxide gas, inside my water. Now that's fun and all, but it doesn't look much like a lava lamp. So let's do that. Grab your bottle. You might need an adult to help you, or maybe a funnel would be appropriate if you think you'll have trouble. And you're going to pour some oil into your bottle. You can choose any size bottle. I like little bottles because they're easier to hold and see. Big bottles are kind of messy, and then you got a lot of oil left over that you can't do much with afterwards. So that's why I like little guys. You're going to fill it up about halfway full. Be as careful as you can to not make any messes. If you do make messes, try and clean them up as quick as you can because oil is very slick and slippery. Alright, and that is about halfway full right there. Now, take a look at your oil. It looks way different than water, doesn't it? You can see it looks like it's thicker. It doesn't look as thin as water. Ooh, what do you think is denser? Oil or water? Remember, the dense ones want to go to the bottom, and the less dense ones want to go to the top. You want to see how it goes? Let's see. I'm going to pour about a quarter, so not completely full, of water. Now, as I pour this in, I notice, oh, the water runs straight to the bottom. Can you see how we have our clear water on the bottom and our yellow oil on the top? The water is denser than the oil, so it wants to sink to the bottom. Now, they're not mixing. They haven't made a solution yet. Let's see if we can shake them up and make a solution. If I give it a good shake, oh, now it's all kind of one color. So we've mixed it together, right? Ooh, maybe not. Watch your bottle carefully. You'll notice that whenever you shook the oil, you made teeny tiny little bubbles of oil. But those bubbles want to stick back together, making bigger and bigger and bigger globs until eventually the oil is all back in one piece at the top and the water is all back in one piece at the bottom. This is because oil and water don't mix. So you guys can see that it's separated back out. Doesn't matter how many times I flip it over, the water wants to go to the bottom and the oil wants to go to the top. Let's take this guy and make him into a lava lamp. So open your bottle back up and let's add some color. I'm going to drip a couple of drops of food coloring in here. Watch what happens as it goes to the oil. It doesn't spread out very much in the oil. That's because it doesn't dissolve in oil. But as it gets all the way down to the bottom, to my water, I'll notice that it starts to spread out a little bit. Why don't we make that go a little bit faster? So we're about to make this guy start bubbling and fizzing like a lava lamp. So take your Alka-Seltzer and break it into small pieces. You want small pieces because we want more surface area. If it's all one big chunk, it's not going to have as much fizzing and bubbling because only one piece of fizz and bubble. This way, we get all of these guys making that reaction. Alright, so I can see that the green has just now reached the bottom of my water and it's stuck kind of in some oil bubbles that are keeping that water from mixing with it. But let's see what happens when we put our Alka-Seltzer in. So grab a couple of chunks and just drop them in right there. And now our Alka-Seltzer starts reacting with the water and we start getting those CO2 bubbles rising up. And there we go. You can see now that the green water is going to start rising up now that it's been able to mix together with our food coloring. And there we go. Can you guys see those big green bubbles that rise up? Because the oil makes kind of a little envelope or bubble around the water because it doesn't want to mix with it. That's how we're able to keep getting these little blobs of color that rise right up. I drop a couple more in there. Can you see them? There's the edge right there. We got a lot of them going up. Now, there's a couple different things we could do to play with this experiment. We could try to do different colors. We could do it in a different size bottle or different shape bottle. Maybe we could mix it up a little bit, use a different type of reaction. We could put some baking soda or maybe some vinegar in there or something like that. As long as you got that acid and base reaction, you'll still end up having this type of effervescent or bubbling quality. Why don't we go ahead and get a whole other tablet and stick it in there. This one was going to do big chunks. Drop them down right there. Now look at the difference that's occurred with our big chunk versus our little chunks. You can see that there's only one bubble coming up, but it's a big one. So, what do you guys think? Was it better with little chunks or better with big chunks? What happened if you crushed it up into a powder and dropped it in or something? Now remember, you want to keep the lid off because if you hear, you get kind of a fizzing sound happening right there. That's that CO2 gas coming up. And I definitely don't want it to come out and make a mess all over the place. This reaction, remember, is getting colder and colder and colder. Makes my water really cold. When the water goes up, it's less dense than oil. Why do you think the water going up is less dense than oil? Remember, less dense things go up. What's inside the water as it goes up? What do we make whenever we have our reaction? That's right, we make CO2 or carbon dioxide. And just like how my balloon is full of air, those are little teeny tiny bubbles that make my water lighter because they're full of that gas or that type of air. They go all the way to the top and they burst, just like the bubbles in your soda. And they let all that air out and they're able to drop back down. That's why we have this up and down all around. It looks like my reaction is slowing down a little bit. Kind of not as big in bubbles as it had been before. The fun thing about this is, now that you've made this, you can keep adding more and more Alka-Seltzer. You don't have to make this again, but every time you drop Alka-Seltzer in here, it'll start making this reaction over and over again until you get to a point where your water has absorbed a lot of the things that are inside of it, and it might not work as well. But you could use this at least 5 or 6 times, maybe more, and you never have to change this water or this oil. What do you think? Try another one? There we go. And it starts up just again. Looking really cool, doesn't it? Wow. What do you think would happen if we used 2 different types of food colorings and then mixed it together like that? How would it look? Oh. I'm going to sit and watch this for a while. I wonder how you guys are going to make this experiment even cooler on your own, though. Thanks so much for hanging out with me today. Hopefully you guys have enjoyed making lava lamps with us, learning about density and chemical reactions. I've been Dusty from Discovery Lab, and thanks so much for hanging out, guys.